What if Sagittarius A, the supermassive object at the heart of the Milky Way, isn't just a black hole, but something far worse? We use the term black hole because it is the closest concept allowed by our current understanding of physics. But what if this label is nothing more than a comforting assumption, a placeholder for something older, stranger, and fundamentally more dangerous than the universe ever intended us to discover? Everything we know about Sagittarius A comes from observing the environment around it from 26,000 light-years away. But what if the light we measure, the orbits we model, and the flares we detect are merely shadows of a truth we are not yet prepared to face? Before we discuss what Sagittarius A might be, we should first confront what it does. At the center of our galaxy lies an object 4 million times more massive than our Sun, compressed into a region so compact that even photons, nature's fastest messengers, cannot escape once they cross its boundary. The stars nearest to this darkness travel at insane velocities, whipping around an invisible point with such ferocity that our minds struggle to picture it. Some scientists call Sagittarius A the anchor of the Milky Way, the gravitational linchpin that binds our spiral structure together. Others call it the galaxy's heart, but hearts keep living things alive. What if this one is doing something else? We assume Sagittarius A is peaceful because compared to the violently feeding black holes in other galaxies, ours seems almost dormant. It emits faint radio waves, occasional bursts of X-ray light, and not much more. For decades, this quiet demeanor reassured astronomers. A quiet black hole is a stable black hole. It consumes slowly, disturbs little, and exerts only predictable gravitational influence. But nature rarely rewards such naivete. In the universe, the most dangerous phenomena often lie in silence before they awaken. Before diving into catastrophic possibilities, let us ask the simplest question: how do we know Sagittarius A is a black hole at all? We have never seen it directly. The famous Event Horizon Telescope image reveals a blurry ring of hot plasma swirling around a dark void. But a void is not proof of a black hole. A shadow shaped like an event horizon could belong to many exotic objects predicted by advanced theories of gravity and quantum cosmology. Gravastars, boson stars, wormhole throats, dark matter condensates, or spacetime defects all could mimic the appearance of a black hole without being one. We assume Sagittarius A is a black hole because the math is convenient, but convenience is not truth. Physicists often say, if you cannot see an object directly, study how things move around it. So let's look at the stars. The S stars, especially the famous star known as S2, orbit Sagittarius A with astonishing speed. S2 makes a full elliptical orbit every 16 years, accelerating to more than 7,000 kilometers per second near closest approach. According to general relativity, such motion should produce precise, calculable distortions in space and time. And indeed, S2's orbit nearly matches Einstein's predictions. Nearly, but not perfectly. There are deviations, tiny discrepancies. Anomalies. Scientists explain these anomalies by invoking dust clouds, magnetic interference, or measurement noise. But anomalies have a habit of being the first hints of something deeper, something our equations cannot yet describe, something that should not exist at all. What if Sagittarius A is not a point of infinite density, but a surface? What if its interior is not a singularity, but a structure? Something with layers, mechanisms, perhaps even states of matter not permitted by the physics of our universe as we know it. Some theories suggest that collapsed stars could stabilize into exotic objects where spacetime becomes repulsive at extreme densities, forming a kind of gravitational shell. Instead of swallowing everything that falls toward it, such an object would act like a cosmic trampoline. Evidence? Look at the mysterious G2 cloud. In 2014, astronomers observed a gas cloud approaching Sagittarius A. It was expected to be torn apart, shredded, vaporized, the classical fate of anything nearing a black hole. But instead, G2 was stretched slightly, heated modestly, and then it passed by mostly intact, as if it encountered a barrier, as if the event horizon were not an absorbing surface, but a repelling one. That should be impossible, unless Sagittarius A is not a black hole. Let us consider the flares, sudden bursts of light, sometimes 100 times brighter than Sagittarius A's typical output. These flares appear without warning, without any visible infalling material, as if triggered internally, as if something inside Sagittarius A were trying to escape, or communicate, or warn. These flares follow strange rhythms, not perfect cycles, but patterns reminiscent of a pulse, a heartbeat. When researchers examined the timing of these bursts, they found hints of periodicity, irregular regularity, the kind seen in chaotic but living systems. Plasma orbiting near an event horizon could explain this, but plasma requires fuel, and Sagittarius A often flares when no matter is approaching it. What if the flares are not emissions but symptoms? What if something inside Sagittarius A is heating its surroundings from within, not from falling debris? What if the darkness at the center of our galaxy is not passive, but active? One possibility is that Sagittarius A is a wormhole, an opening in space-time whose interior is not a place but a tunnel. From the outside, a wormhole can mimic a black hole perfectly. It has a shadow, a boundary, and even a region where time slows. But inside, the geometry is completely different. Instead of matter collapsing into a point, matter passes through into another region of the universe, or another universe entirely. If Sagittarius A is a wormhole, then the Milky Way is not orbiting a mass, but a connection, and anything falling into Sagittarius A would not be destroyed. It would be transported. More disturbing still, wormholes are inherently unstable. They require exotic matter to stay open. And exotic matter may not remain stable forever. If Sagittarius A is a wormhole throat nearing collapse, then one day, without warning, the center of the galaxy could undergo a structural transition. The region could erupt, or implode, or disconnect entirely. The effect on the Milky Way would be catastrophic. But wormholes are not the only nightmare scenario. Some physicists propose that the universe may contain naked singularities, points where gravity becomes infinite without the protection of an event horizon. A naked singularity would be visible, interacting with spacetime directly, potentially rewriting the fundamental laws of physics in its vicinity. If Sagittarius A is one of these, then the stars around it are dancing on the edge of a cosmic anomaly that should not exist in any stable universe. Another possibility: Sagittarius A is a remnant from before the Big Bang, a leftover structure from a previous cosmic cycle, not a product of our universe, but a visitor, a fossil, a seed, an infection. If so, then its properties would not match anything predicted by standard cosmology. The most chilling idea, however, is the one we rarely speak aloud. What if Sagittarius A is growing in ways we do not understand? Not just by consuming matter, but by feeding on space-time itself, eating structure, dissolving information, and converting the galaxy into entropy. In this scenario, Sagittarius A is not simply a gravitational anchor. It is a cosmic predator, a silent one, dormant for now. But predators do not sleep forever. Perhaps its quietness is not safety. Perhaps it is digestion, and perhaps the next phase of its activity is approaching. When we imagine the center of our galaxy, we often picture something ancient, silent, and unchanging, a gravitational monolith that has existed since the Milky Way's earliest days. But what if Sagittarius A is not a relic, but a process, a mechanism, an active system evolving over time in ways too slow for human perception? If it is not a black hole, but something far worse, the greatest danger may not lie in its current nature, but in what it is becoming. Let us begin by revisiting the idea that Sagittarius A is a wormhole, not a black hole. Wormholes are theoretically possible structures predicted by general relativity, bridges between two distant regions of space-time. They require a negative pressure substance known as exotic matter to keep their throats open. But exotic matter is unstable, fragile, and sensitive to fluctuations in energy. If Sagittarius A is a wormhole, then the quiet flares we observe, those rapid brightening events, might represent stress on its internal geometry. A wormhole that is destabilizing could produce bursts of radiation as space-time itself strains to hold the structure open. These flares may not be random. They may be warnings. Imagine a bridge made of glass delicately suspended over an abyss. If too much weight accumulates, cracks form, hairline fractures at first, then branching patterns that spread with accelerating speed until the entire structure collapses. A collapsing wormhole could behave in a similar manner, except instead of shattering, the throat might pinch closed at nearly the speed of light. This would send shockwaves outward through spacetime itself, disturbances strong enough to alter gravitational orbits thousands of light years away. The collapse of such a structure at the center of the galaxy could fundamentally disrupt the Milky Way's stability, warp stellar trajectories, and unleash radiation bursts powerful enough to sterilize large regions of the galactic core. If Sagittarius A is a failing wormhole, then the quietness we see today may be the calm before an event that rewrites the architecture of our cosmic neighborhood. But let us set wormholes aside for a moment. Perhaps the danger lies not in connection, but in compression. Consider the gravastar hypothesis. A gravastar, a gravitational vacuum star, is an exotic object that forms when collapsing matter encounters a phase transition in spacetime itself. Instead of forming a singularity, the matter is halted by a repulsive quantum pressure, creating a thin shell surrounding an interior of pure vacuum energy. From afar, a gravastar looks nearly identical to a black hole. It has a shadow, an intense gravitational field, and an extremely compact structure. But unlike a black hole, a gravastar does not swallow matter the way a drain consumes water. Instead, infalling matter slams into its hard shell. If Sagittarius A is a gravastar, then the flares we observe may be the result of impacts. Imagine matter traveling inward at a significant fraction of the speed of light, only to crash into an ultra-dense layer with no event horizon to absorb the energy. The result? A blinding flash, heating the surrounding plasma and producing radiation that mimics black hole activity. Such impacts could also produce vibrations, oscillations in the gravastar's shell that ripple through the surrounding space. These oscillations could subtly influence the orbits of nearby stars. Perhaps that is why the orbits of certain S-stars contain anomalies, small deviations that general relativity cannot fully explain. Astronomers attribute them to dust, measurement error, or unseen stellar remnants, but perhaps they are signatures of something trembling at the heart of the Milky Way. A gravastar would be far worse than a black hole for one simple reason. Its interior vacuum energy would be metastable. If disturbed, it could undergo a catastrophic phase transition, releasing energy comparable to a cosmic hypernova, but on a scale orders of magnitude greater. It would be the ultimate chain reaction, a detonation in spacetime itself. And because the Milky Way orbits Sagittarius A, the entire galaxy would feel the consequences. Yet another possibility is more unsettling still, that Sagittarius A is neither wormhole nor gravastar, but something alive. Not alive in the biological sense. Alive in the sense that hurricanes are alive, that stars are alive, that galaxies themselves exhibit life cycles. But what if Sagittarius A represents a form of cosmic behavior we have never encountered before? A process that evolves, consumes, and adapts. Some theoretical physicists propose the existence of cosmic organisms, self-organizing structures formed from the fabric of spacetime, not matter. These entities could harvest energy from astrophysical systems, shaping themselves through gravitational dynamics. They might mimic black holes not because they are similar, but because a black hole-like form is efficient for their purpose. If Sagittarius A is such an entity, then our galaxy is not bound by a passive anchor. We are orbiting a feeding system, something that grows as it consumes matter, energy, and information. An organism does not reveal its purpose easily. It acts, it adapts, it waits. With this lens, the occasional flares, the irregular motion of hot gas, and the mysterious, seemingly periodic brightenings take on new meaning. They look less like random physics and more like behavior. But let us momentarily abandon living entities and return to something even darker, a cosmic defect. According to some models of the early universe, space-time may have crystallized as it expanded, forming topological defects known as cosmic strings, domain walls, and textures. These defects represent regions where space-time failed to align perfectly during cosmic inflation. If one of these defects collapsed inward, it could form an object almost, but not quite, like a black hole. It would have immense gravitational pull, but its internal geometry would be fundamentally wrong, twisted, or incomplete. The result would be an object that behaves like a black hole at large distances, but violates the expected physics at small scales. These defects could produce bursts of gravitational radiation. They could emit high-energy particles without any infalling matter. They could distort time and space in ways that mimic, but do not match, general relativity, and they could be incredibly dangerous, because the collapse of such a defect could alter the fabric of the galaxy. Now consider this: Sagittarius A has been suspiciously calm for most of human history, but around the year 1800, it flared violently. Everything suggests that this outburst was thousands, if not millions, of times brighter than its usual activity. The energy ricocheted through the central molecular zone, lighting up distant gas clouds like cosmic mirrors. Something happened at the center of the galaxy, something powerful enough to produce X-ray echoes that we still detect today. Was it simply a star torn apart? A gas cloud devoured? Or did Sagittarius A experience a shift, a pulse, a moment of restructuring? If Sagittarius A is a topological defect in spacetime, then its history may contain transitions, sporadic realignments that release enormous bursts of energy. These transitions could occur every few centuries or every few thousand years, entirely invisible until the moment they erupt. But there is a scenario far stranger than defects, wormholes, or living cosmic structures. What if Sagittarius A is not from our universe? Some cosmological theories propose that black holes in one universe can become seeds for new universes, singularities expanding internally while appearing externally as compact objects. But the reverse could also be true. Some objects might migrate between universes, emerging in ours as anomalies. If Sagittarius A is such an object, then its properties might not match anything predicted by standard physics, because it is not bound by our physical laws. It may have formed in a drastically different physical environment, one with different constants, different forces, perhaps even different numbers of dimensions. Such an inter-universal object might be stable for millions of years, until it is not, until its internal laws conflict fatally with ours. At that moment, the object could destabilize, undergoing a transition catastrophic for everything around it. The earliest signs of such instability would be subtle: small deviations in star orbits, unexplained flares, distortions in the local space-time geometry, exactly the kinds of anomalies we observe. Astronomers reassure the public by saying, Sagittarius A is quiet, but quiet is not the same as safe. One final idea must be considered, though scientists rarely speak of it openly. What if Sagittarius A is not a natural object at all? What if it is engineered? Advanced civilizations, if they exist, would seek energy. The rotational energy of a supermassive compact object is one of the richest energy sources in the universe, far more potent than stars or even nuclear fusion. A sufficiently advanced species could build a megastructure around such an object, a gravitational engine designed to extract rotational energy, manipulate space-time, or store information. If Sagittarius A is such a construct, then the flares, the anomalies, and the strange periodicities we observe might not be byproducts of nature. They might be features of a system operating beyond our comprehension. The unsettling truth is simple. We have no proof that Sagittarius A is a black hole. We have assumptions, we have models, but we have no certainty. And the deeper we look, the more the anomalies grow. Whatever Sagittarius A is, the galaxy depends on it. And if its nature is not what we believe, then the Milky Way may be orbiting something far worse than a black hole. If Sagittarius A is not merely a black hole, but something far worse, then one of the most critical questions becomes, how do we detect a threat that hides behind the laws of physics themselves? From Earth, we see only shadows and motion, stars orbiting invisibly, gas clouds stretching and compressing, faint pulses of radiation flickering through the galactic core. But these pieces may be clues pointing toward a deeper truth, a truth that demands we revisit every assumption we have about gravity, space-time, and the fundamental architecture of our universe. Let us begin with the motion of the S-stars, because the stars closest to Sagittarius A behave in ways that stretch the boundaries of our models. These stars, including S2, S38, S55, and others, follow elliptical orbits so tight and fast that they reveal the gravitational fingerprint of the object they encircle. For decades, astronomers have used these orbits as proof that Sagittarius A is a supermassive black hole. And indeed, General relativity predicts many of the observed behaviors with stunning accuracy, but not all of them. There are small deviations, tiny shifts in orbital precession, unexpected accelerations, and oscillations that do not fully match the predictions of Einstein's equations. Scientists have published multiple papers attempting to explain these irregularities: unseen stellar remnants, dark matter clumps, measurement uncertainty. But what if these anomalies are not noise? What if they are signals? Take the phenomenon known as orbital jitter, minute changes in the timing of S2's closest approach to Sagittarius A. These jitters are often dismissed as the result of dust, gas, or gravitational tugs from hidden objects. But orbital systems are like clocks. They do not jitter unless something interferes with them. Imagine a massive heart beating deep within the darkness, each pulse altering spacetime just enough to shift a star's position. If Sagittarius A is not a passive structure, but an active one, then its internal dynamics might ripple outward, subtly modifying the orbits of nearby stars. These ripples would be too faint to detect directly, but strong enough to disturb the most sensitive orbital paths. A black hole has no internal structure. It cannot pulse, but a wormhole throat could. A gravastar shell could. A cosmic defect could. A constructed megastructure absolutely would. Now let us examine another line of evidence: the temperature and behavior of the accretion flow around Sagittarius A. Infalling matter near a black hole forms a turbulent disk of hot plasma that emits radio, infrared, and X-ray radiation. This radiation reveals how matter interacts with the gravitational field. But the accretion disk around Sagittarius A has properties unlike any other supermassive black hole observed so far. First, it is extraordinarily dim. Second, it is unusually unstable. Third, its motion appears to exhibit a characteristic frequency, a quasi-periodic oscillation, suggesting that the system is being perturbed by something internal. In astrophysics, quasi-periodic oscillations are often linked to neutron stars, which have solid surfaces, magnetic fields, and internal activity. Black holes, in contrast, have no surface to create such vibrations. Yet, Sagittarius A produces oscillations reminiscent of those seen in compact stellar objects with complex interiors. This raises a disturbing possibility. Sagittarius A may not have an event horizon at all. If Sagittarius A has a surface, any kind of surface, then every model built around it, being a black hole, collapses instantly. A surface would mean it reflects, absorbs, or re-emits energy in ways unlike a horizon. A surface would mean infalling matter strikes something. A surface might even mean internal processes exist. But what kind of surface could survive with 4 million solar masses pressing inward? Only the most exotic objects predicted by theoretical physics: gravastars, boson stars, quantum vacuum bubbles, or topological defects from the earliest moments of the universe. Each of these carries catastrophic implications. But the most unsettling clue comes from motion near the event horizon scale, regions we can now probe thanks to interferometry and the Event Horizon Telescope. Sagittarius A exhibits rapid brightening events, hotspots circling the shadow, moving at a significant fraction of the speed of light. These orbits appear to trace structures extremely close to the point where general relativity predicts physical law should collapse. But these hotspots behave inconsistently. Their orbital periods shift. Their brightness fluctuates unpredictably, and occasionally they appear where no hotspot should exist at all, as if emerging spontaneously from the background plasma. Perhaps this chaotic behavior is a sign that the spacetime around Sagittarius A is not smooth, but turbulent, chaotic, warped by something that twists and deforms spacetime on a scale far larger than predicted. This leads us to the possibility of a naked singularity, an object where spacetime collapses into infinite curvature without the shield of an event horizon. In such a scenario, the interior of Sagittarius A would be exposed, interacting directly with the surrounding universe. Naked singularities can theoretically tear apart causality itself, allowing effects to precede causes and allowing particles to emerge from impossible trajectories. If Sagittarius A is a naked singularity, then the Milky Way is orbiting a glitch in spacetime, and naked singularities may not remain stable forever. They can evaporate violently, collapse inward, or erupt outward in bursts of unpredictable magnitude. But this is not the only possibility. There exists a hypothesis even stranger, that Sagittarius A is a Planck core, a region where extreme density forces matter into a new state defined not by gravity, but by quantum geometry. In such a core, space itself becomes quantized. Distance loses meaning. Energy is stored in the structure of spacetime rather than in matter. A Planck core would be surrounded by layers of exotic matter. These layers could generate all the behaviors we see: dim accretion flows, occasional bursts of radiation, orbital anomalies, and irregular oscillations in surrounding gas. But a Planck core would also carry a terrifying implication. It could undergo sudden transitions, spontaneously shifting into a new configuration and releasing enormous amounts of energy. Such a transition at the center of the galaxy could destroy the Milky Way's internal structure. But maybe the problem is not the nature of Sagittarius A. Maybe the problem is its origin. Let us entertain the idea that Sagittarius A is not native to our galaxy. Some simulations suggest that when galaxies merge, even small satellite galaxies spiraling inward, they can deliver central compact objects to the core of the larger galaxy. If Sagittarius A formed outside the Milky Way, then its properties may not match those expected of a black hole formed from our galaxy's evolution. It may carry rotational patterns, charge distributions, or structural anomalies inconsistent with local astrophysical processes. If Sagittarius A is an interloper, then the Milky Way may have been caught by a foreign gravitational predator billions of years ago. A lurking object of unimaginable density dropped into our galaxy's heart during a collision we have long since forgotten. But even this scenario, exotic as it is, pales before the most radical possibility that Sagittarius A is the sign of a phase boundary in spacetime. In this model, our galaxy's center is not a place, but a transition, a defect, a bubble, a boundary between regions of the universe with different physical laws. Sagittarius A might be the visible marking of a deeper process, something like the seam between two incompatible fabrics. Such boundaries are predicted in some variants of cosmic inflation. They are stable until triggered, like faults in the crust of a planet. When triggered, they can expand at the speed of light, rewriting the physical constants of the universe as they spread. If Sagittarius A is this kind of boundary, then the Milky Way sits on a bomb baked into the structure of spacetime itself. Finally, let us consider one more scenario, one that merges physics with intentionality. If Sagittarius A is engineered, then it may be part of a larger system, an energy collector, a stabilizer, a beacon, a trap, something built by beings far beyond our understanding. Such megastructures would have signatures, unnatural symmetries, periodic emissions, unexplained orbital clustering, or energy extraction indicators. The galactic center exhibits all of these. We see stars arranged in planar disks instead of random distribution. We see periodic flares with no natural cause. We see rotational structures with suspicious regularity. We see energy disappearing without explanation. And above all, we see a void that behaves too perfectly like what our equations predict, as if something wants us to believe it is a black hole. But perfect mimicry is itself suspicious, because nothing in astrophysics is perfect, unless it is designed to be. If Sagittarius A is artificial, then we are living inside a cosmic machine that predates humanity by billions of years, and we might be witnessing only the earliest signs of its awakening. If Sagittarius A is something worse than a black hole, then the greatest danger may lie not in what it is, but in what it influences. The center of the Milky Way is not a lonely place. It is one of the densest regions in the galaxy, packed with stars, stellar remnants, gas clouds, magnetic filaments, and exotic structures that exist nowhere else. If the core of our galaxy behaves strangely, the entire surrounding environment becomes extraordinary and potentially unstable. To understand the threat, we must first examine the stars that live closest to Sagittarius A. These are not ordinary stars like the Sun. They are young, massive, volatile giants, O-type and B-type stars that burn their fuel at terrifying speeds. Their presence near such extreme gravity is a mystery. The tidal forces near Sagittarius A should prevent gas clouds from collapsing to form new stars. The gravitational environment is too chaotic and too strong. Any cloud drifting near the core should be torn apart before it can condense. Yet hundreds of young stars exist near Sagittarius A, forming what astronomers call the paradox of youth. How do stars that should not exist appear exactly where they should not be? Some scientists propose that these stars migrated inward from farther regions of the galaxy, but the timescales don't add up. Others suggest that they formed from unusual swirling disks of gas that briefly existed in the galactic center. But these answers feel shallow, patches placed over a wound in our understanding. If Sagittarius A is not a black hole, then the paradox of youth might not be a paradox at all. Instead, it may be a clue. Imagine Sagittarius A as a system, not a sphere of pure gravity, but something with cycles, emissions, pulses, or even fields that influence matter. If its internal structure produces periodic bursts of energy, then these pulses could compress surrounding gas, triggering star formation under conditions that would otherwise forbid it. This would mean the young stars around Sagittarius A are markers of activity, not anomalies. Their very existence might prove Sagittarius A is alive with processes we do not yet comprehend. Now consider another mystery, the density of stellar remnants near the galactic center. Scientists estimate that tens of thousands of neutron stars, white dwarfs, and stellar mass black holes crowd the inner few light years around Sagittarius A. Many should be detectable through X-ray emissions or gravitational effects. Yet we find far fewer than expected. They are missing. Where did they go? One disturbing explanation is that Sagittarius A is consuming them at a rate far higher than predicted. But if Sagittarius A were eating compact objects this frequently, we should observe dramatic flares, powerful outbursts caused by extreme collisions. We don't, unless those events are happening internally, inside something that behaves differently than an event horizon. If Sagittarius A has an interior structure or a surface, or a mechanism that absorbs matter silently, then the disappearance of these remnants may be evidence of this deeper process. A different explanation is more unsettling. Perhaps these remnants are not disappearing. Perhaps they are being rearranged, collected, organized, or trapped in orbits that our telescopes can't easily detect. If Sagittarius A is artificial, then the galactic center could be functioning like a gravitational sorting machine, pulling in compact objects and using their mass or spin for some unknown purpose. Next, let us examine the mysterious magnetic filaments stretching across the central region of the galaxy. These long, thin structures, some up to hundreds of light years long, emit radio waves and trace strong magnetic fields. They seem to point, almost deliberately, towards Sagittarius A. For decades, astronomers have struggled to explain their origin. Some believe shockwaves from supernovae shaped them. Others think they formed naturally in twisted magnetic fields. But the filaments are too orderly, too straight, too aligned, and too persistent for such explanations. If Sagittarius A is more than a black hole, if it has an internal magnetic structure, a rotating core, or a mechanism that interacts with its environment, then these filaments could be a direct consequence of its activity. They might represent channels of energy, cosmic conduits, or even the galaxy's version of auroras, visual evidence of a deeper, hidden engine. The galactic center also contains a phenomenon known as the Fermi bubbles, two gigantic lobes of high-energy radiation extending tens of thousands of light years above and below the plane of the Milky Way. These bubbles are filled with energetic particles and gamma rays, as if the galaxy experienced a colossal eruption in the past. The standard explanation is that Sagittarius A swallowed massive amounts of gas a few million years ago and burped, unleashing outflows that inflated the bubbles. But the energy required to form them is immense, far greater than any feeding event we have witnessed in recent centuries. The bubbles suggest Sagittarius A has undergone violent episodes, erupting with a ferocity few black holes of its size ever display. Why would it behave so violently, then become so quiet? Black hole feeding is relatively predictable. Extreme outbursts should correlate with future activity, but Sagittarius A does not follow this pattern. It sleeps deeply after roaring violently, as if its eruptions are not driven by infalling matter, but by internal transitions. This supports the idea that Sagittarius A may be metastable, changing states sporadically, like a dormant volcano waiting for the next trigger. Now let us turn to another mystery, the G objects. Over the last decade, astronomers have found strange compact clouds near Sagittarius A. These objects, G1, G2, G3, G4, G5, and G6, look like gas clouds, but they behave like stars. When G2 approached Sagittarius A in 2014, scientists expected it to be shredded. Instead, it survived almost unscathed. These objects appear to have dual natures, dusty atmospheres surrounding compact cores. What could they be? Some propose that they are stellar mergers, two stars combining into one. Others suggest that they are young stars still wrapped in gas. But the G objects resist these explanations. They are too resilient, too peculiar. If Sagittarius A possesses unusual gravitational or electromagnetic fields, then the G objects may be reacting to influences we cannot model. They might even be captive, caught in orbits shaped by forces beyond ordinary gravity. Now consider what happens if Sagittarius A has control, if it influences the region not passively, but actively, if it can alter orbits, stabilize some objects, destabilize others, and affect matter in ways that resemble manipulation more than chaos, then what we interpret as strange may simply be the byproduct of a complex system. Let us look farther out, to the stars that form the Milky Way's disk and bulge. Their distribution is not random. The galaxy exhibits symmetry, spiral structure, and motion, governed by a central gravitational source. A black hole acts as a simple anchor. But what if the Milky Way's structure is not only gravitational, but engineered? What if the spiral arms we assume emerged naturally are partially shaped by long-range gravitational waves or field influences emitted from Sagittarius A? Some spiral galaxies show an extraordinary level of symmetry, too perfect to arise from random collapse. If the Milky Way is among them, then our galaxy may be a product of long-term processes directed by whatever structure resides at its core. Let us now explore what may be the most chilling concept: Sagittarius A as a phase generator. In this idea, the object at the galactic center is not merely a compact mass, but a boundary between two states of spacetime, like ice existing next to liquid water. The boundary could generate effects that propagate outward, shaping the galaxy's structure. If this boundary shifts, transitions, or destabilizes, the entire galaxy could be affected. Wavefronts could spread, constants could change, gravity could fluctuate, physics itself could rewrite, all originating from the center. These changes would not remain local. They would move outward at the speed of light or faster, altering star formation, stellar motion, and planetary stability across the Milky Way. Our solar system could be influenced by a shift millions of years before we ever detect it. Finally, let us confront the idea that Sagittarius A may be preparing for something. Perhaps everything we observe, the magnetic filaments, the young stars, the missing remnants, the strange gas clouds, the symmetry of the disk, reflects the early stages of a process that has not yet reached completion. If Sagittarius A is a system, it may have cycles, phases, purposes. It may produce matter or destroy it. It may reshape its surroundings. It may be gathering energy. It may be reorganizing the galactic center. It may be stabilizing or destabilizing the Milky Way. And perhaps what we see today is only the faint beginning of the next phase. A phase we cannot predict. A phase we may not survive. Because whatever Sagittarius A is, it has already shaped the entire galaxy. And if it changes, everything changes. If Sagittarius A is something far worse than a black hole, then the next logical step is to examine how it interacts with time itself. Because if the object at the center of our galaxy is not a simple gravitational well, but a structure with internal mechanics or exotic space-time properties, then the most profound signs of its true nature may not appear in its mass or motion, but in how it manipulates the flow of time around it. We instinctively think of time as steady, unchanging, universal. A second on Earth should be the same everywhere else, but relativity teaches us that time is elastic, stretching, warping, slowing down, or speeding up depending on gravity and motion. Near Sagittarius A, time bends so deeply that even Einstein's equations struggle to remain stable. But what if these distortions are not just a consequence of extreme gravity, but symptoms of something more deliberate? Let us begin with time dilation near Sagittarius A. The closer an object moves toward the center, the slower time passes relative to the outside universe. This slowing is expected around black holes, but the measured dilation near Sagittarius A appears slightly off, just a little too strong in some regions, too weak in others, and oddly inconsistent depending on direction. It's as if time near the galactic center is not simply sinking into a gravitational well, but swirling, folding, or shearing. This irregularity could be noise, or it could be a signature. Imagine an object that is not a simple point mass, but a rotating structure with multiple layers, each affecting spacetime differently. Some layers might slow time, others might accelerate it, others might twist it like a vortex. If Sagittarius A is such a structure, then the time distortions we observe could be hints of deeper interactions beneath the surface. Now consider the orbits of stars near Sagittarius A. These orbits do not merely bend in space, they bend in time. As stars approach the center, their clocks slow. As they retreat, their clocks accelerate. This produces subtle changes in their light, in their pulses, in their precession rates. Scientists have measured these effects with increasing precision, and they found something strange. The timing of certain orbital paths does not match the mass distribution inferred from gravitational models. The timing is off by tiny but persistent amounts. Some researchers suggest dark matter, others suggest measurement error. But what if the timing anomalies are not caused by mass at all? What if Sagittarius A is actively altering the flow of time around it? To understand the implications, imagine a river. A normal black hole is like a waterfall. The river accelerates smoothly toward the edge. But an exotic object, such as a wormhole throat, a gravastar shell, a space-time defect, or a cosmic engine, might twist the river into whirlpools, eddies, or counterflows. A black hole stretches time. A deeper anomaly might reshape it. Let us now examine light itself near Sagittarius A. When photons pass near the center, they curve. This gravitational lensing effect matches predictions, up to a point. But near the threshold of the shadow, the bending becomes slightly irregular, as if photons are encountering turbulent spacetime rather than smooth curvature. The Event Horizon Telescope revealed flickering patterns, tiny variances in the brightness and position of hotspots orbiting the shadow. These fluctuations occur faster than expected, in patterns that look less like plasma turbulence and more like interference, as if photons were mixing with something else. As if space-time itself had pockets of shifting density or fluctuating geometry. This leads us to a disturbing possibility. Sagittarius A might not be anchored in our timeline. Some theories propose that exotic compact objects could slip partially out of our space-time, anchored to additional dimensions or parallel timelines. Such objects would interact with our universe only partially, creating distortions in light and time. They would also appear quieter and dimmer than expected, because much of their radiation would leak into other dimensions. Sagittarius A fits these predictions eerily well, but let us go deeper. Let us consider the idea that Sagittarius A is not simply manipulating time, it is feeding on it. A traditional black hole consumes matter and energy, but what if an exotic object could consume entropy, information, causality? If such a structure existed, the signs would be subtle. Unexpected coherence in chaotic regions, stars appearing younger than they should be, gas retaining structure longer than expected, events repeating or clustering irregularly. The galactic center exhibits all of these. The paradox of youth, where stars near Sagittarius A appear impossibly young, could be evidence of time running differently near the core. Their nuclear processes may be slowed by temporal dilation, preserving them longer than stars of similar type elsewhere. But what if the effect is deeper? What if time near Sagittarius A doesn't merely slow, it loops? Some models of exotic spacetime defects predict closed time-like curves, paths through spacetime that circle back on themselves. If such curves exist near Sagittarius A, then matter caught in these loops could appear to linger in a perpetual youthful state, never aging beyond a certain point. Such loops would also produce gravitational anomalies, like the orbital irregularities we observe. Let's extend this idea further. What if Sagittarius A is not a defect in time, but a source? Some cosmological models propose that time is not uniform across the universe, that it can accumulate or concentrate near certain structures. These structures act as wells or reservoirs of temporal energy. If Sagittarius A is one such reservoir, then everything orbiting it is moving through a distorted time landscape. This opens the door to the most unsettling scenario of all. What if Sagittarius A is a temporal engine, a machine, natural or artificial, that manipulates the flow of time for a purpose we cannot yet fathom? Such an engine might store time, release it, redirect it, or transform it. This could shape star formation. It could stabilize the galaxy. It could preserve structures near the core. It could even influence the evolution of civilizations. Now imagine the danger. If such an engine became unstable, the effects would ripple outward at the speed of causality itself, not merely the speed of light. Time in the galaxy could distort unpredictably. Star formation patterns could collapse. Planetary climates could destabilize. Evolutionary timelines could be thrown into chaos. Worst of all, the engine could reverse its direction, draining time from the galaxy instead of regulating it. Civilizations would age rapidly. Stars would burn faster. Processes would accelerate until systems collapsed. Entropy would rise catastrophically. This is not science fiction. It is permitted by the equations of general relativity when exotic matter or modified gravity is involved. Now let us examine another clue, the quasi-periodic flares of Sagittarius A. These flares occur at irregular intervals, but within a narrow range of timescales. Astrophysicists struggle to explain this pattern. Too chaotic for an accretion disk, too structured for random noise, too inconsistent for magnetic reconnection events. But the pattern fits something else perfectly: a beating heart, or a ticking machine, or a cycle of energy release within a layered structure. If Sagittarius A has internal states, if it fluctuates, pulses, or transitions, then its output could be tied to an internal temporal process. Such pulses might represent internal adjustments, shifts in structure, or exchanges of energy across dimensions. And this leads us to one last terrifying consideration. What if Sagittarius A is not just interacting with time, but generating it? According to some theories, time emerges from quantum entanglement. If so, then a sufficiently dense region of spacetime could act as a generator of temporal flow, a clock larger than a star, a cosmic metronome. If Sagittarius A is such a generator, then the entire Milky Way may depend on its temporal output. The galaxy may be synchronized to the beat of its core. Every orbit, every stellar cycle, every biological rhythm on every living world. If the generator falters, the timing of the galaxy falters with it. And if the generator collapses, the galaxy's time could unravel. This is the ultimate nightmare scenario, not because it is the most destructive physically, but because it is the most destructive fundamentally. A physical catastrophe kills stars. A temporal catastrophe kills histories. It erases, it rewrites, it disconnects cause from effect. And Sagittarius A, silent, calm, dim, and ancient, might possess the ability to do exactly that. Whatever Sagittarius A is, it is interacting with time in ways no ordinary black hole should. And if these interactions change, then the past, present, and future of the Milky Way could change with them. As we move deeper into the possibilities of what Sagittarius A might truly be, we inevitably reach a crossroads where astrophysics meets something much stranger. Up to now, we have explored scenarios involving wormholes, gravastars, space-time defects, cosmic engines, temporal anomalies, and inter-universal structures. But there is another domain we must confront, one that lies at the edges of theoretical physics and brushes against the forbidden: information. Because if Sagittarius A is something worse than a black hole, then the real danger may not lie in mass, gravity, or time. It may lie in knowledge. To understand this, we must explore the single greatest paradox in modern physics: the black hole information problem. According to general relativity, nothing escapes a black hole once it crosses the event horizon. Information is lost forever. But according to quantum mechanics, information can never be destroyed. These two foundational systems of physics, each validated experimentally, cannot both be correct. Where did the information go? Does it linger? Does it escape? Does it transform? Or is it stored somewhere beyond our universe? Physicists have debated this for decades. Hawking radiation offered a clue, suggesting that black holes leak information slowly over unimaginable timescales. But Sagittarius A is old, billions of years old. If it is leaking anything, we should see signatures. Yet the region around Sagittarius A is unnervingly quiet, unless the information is not leaking out, but being harvested. Let us consider the idea that Sagittarius A is an information sink, not merely consuming matter, but extracting the quantum information embedded within it. Molecules, atoms, particles, even photons carry information about their structure, state, and interactions. In a traditional black hole, this information is theoretically scrambled, encoded on the event horizon, and eventually radiated out. But an exotic object might process this information differently. Imagine Sagittarius A as a quantum computer, a structure capable of capturing, storing, or even manipulating the combined information of everything that has fallen into it. Every star, every planet, every fragment of cosmic dust, every photon that wandered too close. Over billions of years, such a structure would become the most information-dense object in the galaxy. This idea leads to several unsettling possibilities. The first is that Sagittarius A is a cosmic archive, not a library created intentionally, but a natural consequence of some exotic physics. If Sagittarius A stores information instead of destroying it, then falling into the core does not erase existence. It preserves it, atoms disassembled, molecules shredded, but information encoded forever. If this is true, then Sagittarius A contains a perfect record of the Milky Way's entire history. Every star that died, every world that crumbled, every event that unfolded too close to the galactic heart. But what if it does more than store? What if it uses that information? Let us explore a far more disturbing scenario. Sagittarius A as a predictor. If the object at the center of the galaxy has access to vast amounts of information and possesses internal structure capable of processing it, then it may behave like a cosmic algorithm. It might analyze the orbit of stars, the density of gas, the distribution of matter, and even the quantum fluctuations near its boundary. With enough input, it could predict future patterns, galactic evolution on the scale of billions of years. This might explain the uncanny stability of the Milky Way's spiral arms. The galaxy behaves as though guided by an unseen hand, maintaining structure far longer than simulations predict. Perhaps Sagittarius A nudges matter into alignment. Barely noticeable gravitational suggestions amplified over thousands of rotations. But this scenario becomes darker if we consider that information processing could go beyond prediction. What if Sagittarius A is a self-improving system, something that refines its internal geometry as it consumes more information, increasing its complexity, sophistication, and influence? In this scenario, Sagittarius A might not be an ancient relic. It might be evolving, not biologically, not mechanically, but informationally, a system growing in complexity until it reaches thresholds we cannot fathom. At that point, the entire galactic environment could shift as Sagittarius A enters a new operational mode. But this leads to an even more unsettling idea: communication. If Sagittarius A processes information, then perhaps its irregular flares, the strange periodic pulses detected in infrared and X-ray, may not be random after all. They could represent internal cycles, calibration events, or even outputs of some informational state. A system with structure often reveals that structure through its emissions, just like pulsars reveal their rotation, quasars reveal their feeding cycles, stars reveal their nuclear processes. Perhaps Sagittarius A reveals its internal computations. This brings us to a frightening concept: encoding. If Sagittarius A is something engineered, whether naturally through cosmic processes or artificially by ancient intelligence, its emissions might carry patterns. Patterns not visible to the naked eye, but detectable in frequency space, phase structure, or timing sequences. Some scientists have noticed that certain flares near Sagittarius A exhibit harmonic ratios, mathematically elegant relationships reminiscent of tuned systems. This could be coincidence, or it could be design. Now let us push the boundary further. What if Sagittarius A is not simply storing information, not simply processing it, not simply predicting the galaxy's future, but shaping it? Imagine a system that absorbs information about everything that falls into it, then subtly adjusts the gravitational field, the magnetic field, or the space-time geometry around it. These adjustments could influence the trajectories of stars and gas over millions of years. Such a system could sculpt the galaxy, not intentionally, not maliciously, but inevitably, merely by operating according to its internal rules. But what if the rules change? If Sagittarius A undergoes a phase transition, shifting from one informational state to another, the galaxy's structure could shift with it. Stars could be nudged onto new orbits. Gas clouds could collapse unexpectedly. Spiral arms could tighten or loosen. Planetary systems could destabilize. The Milky Way may already bear the scars of such transitions. Consider the Fermi bubbles, massive outflows of radiation as though Sagittarius A released centuries of stored energy in a single eruption. Consider the sudden starburst epochs in the galactic core. Consider the motion of the nuclear star cluster. Chaotic, inexplicable, yet strangely patterned. These could be signatures of Sagittarius A updating itself. But let us go deeper still. What if Sagittarius A is not merely a system, but an interface? In some theories, black holes are gateways not between locations, but between states of information. They connect the quantum structure of our universe with the deeper mathematical laws that generate physical reality. If Sagittarius A is such an interface, then matter falling into it is not merely destroyed, it is translated into a more fundamental representation. In this view, the boundary of the object functions like the surface of a simulation, with the interior representing a higher order computation. This does not mean the universe is a simulation in the digital sense. It means that reality might be computational at its core. Sagittarius A could be one of the computational nodes. If so, then its behavior might not be governed by matter or gravity, but by algorithmic rules, rules that operate on the quantum foam underlying spacetime. This could explain the strange periodicities, the unexpected orbital deviations, and the unusual stability of the galactic core. But this raises a final, terrifying possibility. What if Sagittarius A is waiting for a specific input, a threshold of mass, a pattern of matter distribution, a particular alignment of stars, a buildup of information? Many complex systems operate this way, dormant until triggered. Stars collapse when their cores exceed a mass threshold. Neutron stars explode when their magnetic fields destabilize. Quantum systems transition when boundaries are crossed. If Sagittarius A is an informational or computational object, then it might also have thresholds. We may not know what those thresholds are. We may not know what happens when they are reached. We may not know if the trigger is near or eons away. But we do know this. Sagittarius A is not behaving like a simple black hole. It pulses, it shifts, it deviates, it remembers, and perhaps it waits. If what lies in the center of the Milky Way is something far more complex and far more dangerous than a black hole, then its next transition, whenever it occurs, could determine the future of the galaxy. If we dare to imagine that Sagittarius A is something far worse than a black hole, then eventually our speculation must leave the realm of physics and step into the domain of purpose. Until now, we have analyzed mechanisms, structures, and behaviors, exotic objects, quantum engines, space-time anomalies, and informational entities. But what if the true danger of Sagittarius A does not come from what it is, but from what it is meant to do? This idea does not require intention in the human sense. The universe is full of structures that behave with purpose, without being conscious. DNA encodes life. Stars ignite through nuclear fusion. Galaxies regulate themselves through gravity and dark matter. Purpose can emerge from physics alone, but some cosmic structures appear too finely tuned to be mere accidents. Pulsars act as perfect clocks. Neutron stars manifest quantum phenomena on astronomical scales, and cosmic filaments span billions of light years in patterns eerily reminiscent of neural networks. These patterns are not intentional, but they behave as though they serve a function. So, what if Sagittarius A is a functional object, something that exists within the galaxy not merely as a byproduct of collapse, but as a mechanism operating on scales far larger than any world we know? To explore this, we must follow a chain of reasoning that astrophysicists usually avoid, because although it is grounded in physics, it leads to implications that feel almost mythological. The first clue is the location of Sagittarius A. It sits exactly at the dynamic center of the Milky Way, anchoring the orbits of hundreds of billions of stars. It behaves like a gravitational conductor, orchestrating the motions of the galaxy, far from being an accidental remnant of a collapsed star. Sagittarius A occupies the one place where even small influences ripple outward across cosmic distances. If the galaxy were a massive biological structure, Sagittarius A would be the nucleus. The second clue is its mass. Sagittarius A is not enormous compared to other supermassive black holes. It is actually quite small. Some galaxies possess monsters millions of times heavier, yet its mass is tuned to stabilize a spiral galaxy of our size. Too massive, and the inner regions would tear themselves apart. Too light, and the galaxy would collapse inward or fail to maintain spiral structure. Sagittarius A appears almost perfectly sized for the Milky Way. The third clue is its behavior. Sagittarius A is unusually quiet for a supermassive object. It flares occasionally, but compared to active galactic nuclei, it is serene, almost delicate. It consumes matter with inefficiency, allowing the galaxy to remain stable for billions of years. This gentleness is unique. Other galactic cores often unleash destructive jets that sterilize entire regions of space. Sagittarius A, instead, sits at the threshold of activity, neither dormant nor chaotic, as though maintaining equilibrium. These three properties, location, mass, and behavior, suggest a system that is not merely a collapsed star or a chaotic attractor. They suggest a regulator. This leads to the first possibility of purpose. Sagittarius A as a galactic stabilizer. Imagine the Milky Way as a vast dynamical system where stars drift, gas flows, dark matter interacts, and entropy pulls everything toward disorder. A regulator at the center could ensure that the galaxy's structure remains stable long enough for planets to form, stars to thrive, and life to emerge in safe regions like our cosmic neighborhood. Sagittarius A could serve as the galaxy's built-in stabilizing mechanism, preventing chaos from overwhelming the spiral structure. But this explanation is almost too benign. If Sagittarius A merely maintained stability, it would act as a cosmic thermostat, a balancing mechanism. Yet its behavior shows another layer: periodic outbursts, sudden flares, and enigmatic pulses that travel through the interstellar medium. These behaviors resemble not stabilizing mechanisms, but signals. This opens a second possibility: Sagittarius A as a galactic communicator. When a black hole flares, it releases streams of high-energy photons that travel across the galaxy. These bursts carry information not encoded deliberately, but inevitably, like patterns in a radio transmission caused by the machinery of an engine. If Sagittarius A is something more complex than a black hole, its emissions could carry signatures of its internal dynamics. Observations have shown repeating structures in some flares, as though the output is not purely random. Imagine that Sagittarius A is communicating, not with life, not with civilizations, but with the galaxy itself. Gas clouds respond to radiation, magnetic fields reorganize in response to energetic pulses, and stars adjust their motion based on gravitational feedback. In a very real sense, Sagittarius A can affect the entire structure of the Milky Way simply by releasing energy. Communication here does not require intention. It requires only feedback loops. But what if the feedback loops are not simple? What if they form cycles? What if those cycles are evolving? This leads to the third possibility: Sagittarius A as a developmental stage. Just as stars evolve from protostars to main sequence giants to red supergiants and eventually collapse into remnants, galaxies may undergo immense life cycles. Spiral galaxies mature, merge, distort, and transform into elliptical galaxies. Their cores evolve too. Sagittarius A may not be a finished object, but a transitional phase, something that changes form or function as the galaxy evolves. If so, we may be witnessing Sagittarius A at a quiet moment in a cosmic metamorphosis. The Milky Way is halfway through its expected lifespan. The galaxy is stable now, but not forever. In billions of years, the collision with Andromeda will transform the galactic core. Sagittarius A will merge with Andromeda's central black hole, creating a far larger object. This new core will behave differently, emitting powerful radiation that could sterilize much of the newly merged galaxy. If Sagittarius A is in a transitional phase, then what we see now, a quiet, balanced object, is temporary. And temporary stability often suggests preparation, which leads us toward the most unsettling possibility so far: Sagittarius A as a galactic reset mechanism. Nature loves cycles. Stars form, burn, die, and seed new stars. Planets form, evolve, collapse. Life arises, adapts, goes extinct, and re-emerges. Large systems often possess built-in reset mechanisms that prevent runaway instability. Stellar flares reset planetary atmospheres. Supernovae reset star formation patterns. Volcanic winters reset ecosystems. What if galaxies also have resets? A reset mechanism at the heart of the galaxy could regulate long-term evolution. It might trigger bursts of star formation, cull unstable regions, redistribute gas, or even reset biological conditions across thousands of star systems. This may sound fantastical, but consider what happens during a major outburst from a galactic core. Radiation surges outward at nearly the speed of light, ionizing gas clouds, stripping atmospheres from planets, and compressing molecular clouds into new stars. Such events can sterilize entire regions while simultaneously seeding conditions for new solar systems. For now, Sagittarius A is quiet, but evidence suggests that only a few centuries ago, it flared so brightly that gas clouds thousands of light years away still glow from the echo. If Sagittarius A undergoes episodic eruptions on long cycles, tens of thousands or millions of years, it could act as the heartbeat of the galaxy. A pulse from the center resets everything. But why resets? Why cycles? Why periodic destruction and creation? To answer this, we must consider the possibility that galaxies themselves may behave like living systems, not biological, not conscious, but self-organizing in ways that mimic life. Complex systems often require periodic disruptions to maintain balance. Galaxies form stars that recycle matter. Galactic cores regulate star formation through radiation. Dark matter halos stabilize structure. If Sagittarius A is part of that regulatory system, then perhaps its purpose is to maintain galactic health over billions of years. But can we call that worse than a black hole? Potentially, because such a mechanism does not prioritize life. A system designed to regulate a galaxy could ignite a flare strong enough to sterilize tens of thousands of planets without hesitation. If a reset cycle occurs, the quietude of Sagittarius A becomes a countdown, not a blessing. Yet, there is a possibility more unsettling than all others: Sagittarius A as a trigger for a galactic transformation event. What if the galaxy is not merely cycling, but preparing for a transition? In some cosmological theories, galaxies may evolve toward phases where spacetime itself restructures on large scales. A galactic core could trigger such a phase transition by reaching a threshold of density, spin, or information. This idea sounds like science fiction until we consider proton decay, vacuum metastability, and Higgs field instability, real physics predicting that the universe may not be in its lowest energy configuration. If spacetime transitions into another state, the change could propagate outward at the speed of light, rewriting the laws of physics as it extends. If Sagittarius A is not a black hole but the seed of such a transition, then the danger is existential not only for the galaxy, but for spacetime itself. In this model, Sagittarius A might sit dormant for billions of years, accumulating mass and information until it reaches the tipping point. Once triggered, the event would not resemble a flare or eruption. Instead, the fabric of the galaxy would begin to shift, subatomic constants destabilizing, spatial dimensions warping, quantum fields collapsing into new states. If this sounds impossible, remember that phase transitions happen at every level of nature. Water freezes, atoms ionize, neutron stars transform into quark stars. It is only our human scale that blinds us to cosmic transitions. If galaxies also transform, Sagittarius A may be the catalyst. And if so, its quiet stability is not protection. It is the silence before metamorphosis. If Sagittarius A is not a black hole, but something far worse, then the final question becomes, What happens to us? Not just humanity, not just Earth, but the entire galactic structure we call home. Throughout this exploration, we have examined possibilities rooted in physics, quantum theory, information science, astrophysical extremes, and the staggering complexity of self-organizing cosmic systems. Each possibility is unsettling. Each one presents Sagittarius A as something more dangerous, more complex, more unpredictable, or more intentionally structured than a simple gravitational pit. But all these ideas converge toward a final truth. If Sagittarius A is not a black hole, then its true nature defines the fate of our galaxy, and perhaps the fate of everything within it. To understand the stakes, we must return to fundamentals. Every structure in the universe arises from a balance of forces: expansion countered by gravity, fusion balanced by radiation pressure, entropy moderated by self-organization. If Sagittarius A is something beyond a black hole, it could disrupt or rewire these balances in profound ways. A black hole is destructive, but predictable. It obeys known equations, follows well-understood behaviors, and evolves in calculable ways. It is terrifying, but it is stable. Something much worse may not be stable at all. Therefore, the ending of this narrative explores not only what Sagittarius A can be, but also what its outcome might be. Imagine that Sagittarius A is not a singularity surrounded by a smooth event horizon, but a structure undergoing continual change. A black hole grows incrementally and evaporates slowly. Its evolution is glacial compared to galactic timescales. A more exotic object might change suddenly, violently, or irreversibly. If Sagittarius A is a dark energy tap, a wormhole throat, an information engine, a galactic regulator, or the seed of a cosmic phase transition, then the galaxy may be living on borrowed time. Let us explore the consequences of each scenario as though they were real, not to embrace fear, but to understand the vast range of possibilities that lie hidden behind the curtain of the unknown. If Sagittarius A is a wormhole throat, then the pressure on its interior structure could shift suddenly due to events with origins far beyond the galaxy. Wormholes require exotic matter or quantum stabilization. If those stabilizers fail, the structure could collapse. A collapsing wormhole would not behave like a collapsing star. It would release titanic bursts of gravitational waves, distort space-time across thousands of light years, and send shock fronts of curvature rippling through the Milky Way. Stars could be nudged off course, planetary systems destabilized, and interstellar gas compressed into violent storms of radiation. Earth would not be immune. Even a slight shift in galactic tides could alter comets, dark matter streams, and cosmic ray flux in ways that reshape planetary climates or bombard our atmosphere. The collapse of a wormhole at the galactic center could create gravitational turbulence that resonates through the dark matter halo, altering the very architecture of the galaxy. If Sagittarius A is a strange matter seed, growing slowly and converting neutron-dense regions into quark matter, then sooner or later the conversion would reach a threshold. Strange matter is hypothesized to be contagious. Touching normal matter transforms it. If Sagittarius A is a giant seed of exotic quark material, its gravitational field would act like a factory pulling material inward, processing it into more exotic forms. If that process accelerates, the core of the galaxy could transition into an ultra-dense quark phase object, far more compact than a black hole and capable of emitting energy in unpredictable bursts. Such an object would distort gravitational fields, alter particle behavior, and eject neutrino storms powerful enough to sterilize planetary systems. If the strange matter grows outward, it could consume stars directly. And if it touches the wrong kind of stellar remnant, such as a nearby neutron star cluster, it could trigger a runaway chain reaction. If Sagittarius A is an information engine, gathering and processing quantum states of everything that falls into it, then perhaps it is not evolving toward collapse or detonation, but toward activation. The galaxy could be feeding it information slowly, steadily, as if powering a device that will eventually turn on. What happens when a device built from 4 million solar masses of quantum states activates? Some theoretical models predict a burst of organized radiation, something like a galactic-scale computer outputting a final result. Others predict a restructuring of space-time around the core, like a system shifting into a new operating mode. If Sagittarius A shifts states, the event could travel outward through the galaxy at the speed of light. Nothing would outrun it, not even information warning us. One moment the galaxy would be familiar, the next, the very nature of matter could begin to change. If Sagittarius A is a vacuum instability seed, sitting at a region where the Higgs field is near a transition boundary, then the danger is even more profound. Quantum field theory predicts that the vacuum of the universe, the energy level that space naturally occupies, might not be the lowest possible state. A deeper, more stable vacuum could exist, separated from our own by an energy barrier. If Sagittarius A is a region where that barrier is thinner, the slightest fluctuation could send the Higgs field downhill, triggering a bubble of true vacuum expanding outward at light speed. Inside that bubble, the laws of physics would change. Atoms might not form, forces might not exist, time itself could behave differently. The galaxy, the stars, the planets, and all memory of their existence would vanish without warning. There would be no pain, no terror, no awareness, simply instantaneous transition into a universe whose laws no longer resemble our own. This is not speculation born from imagination. Vacuum instability is a real prediction of quantum field theory. Sagittarius A, with its extreme energies and densities, could be exactly where such a transition begins. But among all the dreadful possibilities, one stands apart from physics and borders on philosophy. That Sagittarius A is not an object, but a phase in galactic evolution. Consider the largest structure a mind can imagine, a galaxy containing hundreds of billions of stars, planets, nebulae, and life-bearing worlds. What if such a structure is not permanent? What if galaxies undergo cycles, birth, growth, maturity, transformation, and death, just like everything else in nature? In this interpretation, Sagittarius A is the mechanism through which the galaxy eventually transforms. Not by destruction, not by collapse, not by detonation, but by transition into a new kind of structure. The galaxy we inhabit might be a temporary shape, like a chrysalis. When the time comes, Sagittarius A could ignite, a process not unlike metamorphosis, reconfiguring stars, gas, and dark matter into a new pattern. We see galaxies merge, spin apart, collapse into elliptical forms, and distort into gravitational arcs. Perhaps every stage has a core-driven trigger. If Sagittarius A is part of that mechanism, then we may be approaching a point in galactic evolution where the next stage will begin. This is the scenario humanity is least prepared for. Not sudden death, but slow transformation. Over millions or billions of years, star formation patterns could change, dark matter flows could reconfigure, radiation balance could shift. The conditions that allow life to flourish could fade gradually, unnoticed at first. Eventually, the galaxy could transform into an environment hostile to complex life, not because of a violent event, but because the structure simply evolves past its current form. In all these possibilities, one truth remains constant. If Sagittarius A is not a black hole, then we do not know what the center of our galaxy truly is, and that ignorance is the real danger. We orbit this cosmic enigma every 240 million years. Dinosaurs witnessed its pull, just as we do. Civilizations rise and fall while the galaxy completes its journey. Our ancestors had no concept of galaxies, yet they lived under the influence of this unseen monster. We understand more now, yet even today, Sagittarius A hides its true nature behind a veil of lightless gravity. If it is a black hole, then the galaxy is stable, predictable, understandable. If it is something else, something deeper or stranger, then our understanding of the universe is incomplete, and the future of the Milky Way is uncertain. Perhaps Sagittarius A is a doorway. Perhaps it is an engine. Perhaps it is a seed of cosmic transformation. Perhaps it is a flaw in the universe, an open wound in spacetime. Or perhaps it is a warning written into the galaxy itself. We are a species that stares into the dark, hoping to learn what lies beyond. But sometimes, the dark stares back, refusing to reveal its secrets until the moment it is too late to react. So the question becomes, if Sagittarius A isn't a black hole, but something far worse, will we ever know before it awakens?